All right. Yeah, another salmon on the mic. Oh, yeah, yeah. So, yeah, we're looking at the proton, yeah, and you look at the shape of the proton, yeah, and in some of my most recent videos, I've been talking to you about how the meter, the most basic of all units of measurement, the measurement of length, where I was hinting on the suggestion that the meter itself can't be can't be constant, can never be constant. Yeah. Now, going deeper into that argument, I like to consider science from a voyeuristic point of view. I could get deep if I concentrated, if I wanted to, but that's not my desire right now. And I have proven myself to be somebody who, when I put my mind to it, I can become a master of science. So, but right now, I'm doing it voyeuristically or voyeuristically, yeah. So I'm just gonna basically float along the theories we have there in mainstream. These, I mean, you got to appreciate science because science, although it's not most scientific or mathematical concepts from mathematical theory will never be realized. Like E equals mc squared is something that will never be realized. It's a theoretical max energy that you can obtain from a mass. Yeah, but it's in reality we haven't even come close to extracting that much energy out of a given mass. Yeah, and we never will get there. Even Einstein admittedly said that we'll never actually see E equals mc squared anywhere in real life. Yeah, so but you got to appreciate theoretical mathematics and physics because they create the framework. If anything, they initialize the situation, and from there we can actually build towards a theoretical limit which we can only reach with certain properties being infinity. But those are things we can't really realize from a classical physics point of view. Yeah, so when I criticize theoretical physics, I'm not saying it's not important. It's very, very important. It's very important to have a rough idea of what something is before you can actually get to an accurate value. It's very, very important. But you can't take theoretical physics and theoretical maths as proof of anything in real life. Yeah? Because there is, in real life, there's nothing that is constant. Even the meter itself depends on the diameter of an atom. Yeah? And the diameter of an atom depends on the diameter of the nucleus. Yeah? And the constituents of the nucleus, which are the proton and the neutron. So the diameter of a given atom can never be constant. There is, I mean, if you look, the reason, there's two reasons I see, two reasons. Yeah. First of all, when measuring, I'm reading from pbs.org. It's just I was doing some research on the shape of a proton just to see what kind of fluctuations we expect when we try to measure the diameter of a proton. So when measuring the proton's shape, measuring the proton shape has also led to some interesting results based on theoretical calculations in nuclear physics and scattering experiments like those used to measure proton size. We know a proton is indeed spherical, or rather spherical-ish. Alright? Meaning it's not really a perfect sphere. So even the proton itself cannot give you a perfect circle. The perfect circle does not exist anywhere in real life, only in theoretical physics and math. It's never something you would ever realize physically. So the most basic of particles, the proton, even that one is spherical-ish. Yeah, spherical-ish. the shape fluctuates. The shape fluctuates. Yeah, around the spherical average. Yeah, and those non-spherical flickers arise from the quarks and other bits inside the proton. While the fluctuations may take many forms, the dominant ones are either peanut shape or bagel shape. Yes. So we get that. Right. So because the shape of a proton can never be a perfect sphere, when two protons are brought into alignment, in some instances, when you bring two protons into alignment, they might be a little bit farther away or a little bit closer, depending on the fluctuations of the what do they call them? Of the quarks inside it. So if a quark is really sticking out, then when they come together, they'll be a bit farther out. If the quark is just barely sticking out, when they come together from this side, they'll be closer. So even aligning protons adjacent to each other has fluctuations. Yeah. Now, when you measure a meter, yeah, you are dealing with how long is a meter, right? Now, if you was get down to what to the visible eye would be one dimension, which is just a protons aligned together, yeah, to be as where the alignment is as long as a meter, yeah. In terms of hydrogen, if you bring hydrogen, one hydrogen atom, you align them adjacent to each other until you make a string that is 1 meter long, you're gonna need, if you look at the radius of a proton, yeah, it's given here in fermions, yeah. Oh, sorry, not fermions. What do I call it? Femtometers, yeah, right, which are 10 to the minus 15 of a meter, yeah. So the radius is about that, yeah, 8.768. So the diameter must be around 17.536 or whatever it is, yep. Right, so the diameter also fluctuates by that, right? Yeah, which is in femtometers, yeah. So sometimes the actual diameter of the proton determines the diameter of the hydrogen atom, and it does this, yeah, fluctuates between 0.0069 femtometers minus or plus, yeah. So it does that. So even when you bring them together, there's also a fluctuation, yeah, as well as the distance of adjacency, yeah. So your meter will have, if it's based on a hydrogen atom, where you could say it's around the diameter of a proton, or 2 times that if you like, if you include a neutron, yeah. So but with the fluctuation, yeah. So you need 2 times that to the power of that, yeah, right, which is around 1.6 femtometers, yeah. So you need, to get 1 meter, you need 10 to the 16 atoms of hydrogen to be aligned adjacent to each other to make an equivalent of 1 meter. Now when you have 10 to the 16 hydrogen atoms aligned together, the string will be as long as 1 meter, yeah. But because it has these fluctuations, you're gonna have to multiply that yeah, by itself, yeah. So it's 1 atom, so that error and that error and that error and that error yeah, to get the fluctuation Yeah, as well. Yeah. Sorry. I was doing a mix up of probability and uncertainty. So it will have a fluctuation. Yeah. And every time you measure a meter, every time you measure 10 to the 16 hydrogen atoms aligned to make a meter, you get a different answer every time because of this fluctuation, because the diameters change and they mix with each other. Yeah, there are different phases as well. Yeah, but you're not gonna get the same meter every time you measure it. So even the meter is not constant. Yeah. The fluctuations might be in the order of femtometers. Yeah. So let's say 10 to the minus 16 is the order of the fluctuations for the measured meter. Yeah. This means that if you look at every physical constant of the universe, yeah, if I go to physics info, yeah, every constant in the universe, I don't believe in constants. Yeah. So the speed of light can never be constant because it's given in units of meters, and we know that each meter is fluctuating. So if each meter is fluctuating, the speed of light fluctuates too. Yeah, but I think they know that it fluctuates around an average. So this is more of an average value than a constant. Yeah. If the meter is fluctuating, that's fluctuating. Yeah, we'll come to that. It's basic reasoning. Anything that's got a meter in it, joules are Newton meters, so Newton meters per second. Anything that's got a meter in it cannot be a constant. All these things, this one hasn't got a meter in it. All these things have a meter in it, so therefore all those universal constants cannot be constant. They're averages. Yeah. Oh, that's got a meter in it. That's got a meter in it. I could tell you where you're going wrong. Everywhere you have a constant that includes a meter in it, there's a fluctuation in it based on what I just said at the beginning of this video. Yeah. Standard gravity, that's not gonna be a constant. I don't know why you even have that as a constant. Hubble constant, no, it's got a meter in it. Yeah, so that's gonna be a fluctuation. Yeah, there's no such thing as a universal constant that contains a meter, but all the other things also fluctuate too. Yeah, and that's just me telling you that the joule is a Newton meter. Yeah. Now I look at the sun and I see what it's composed of. Yeah. Now if we use uncertainty principles and the fluctuations, yeah, the size of this of the sun fluctuates. But we'll come to that. That's just too many uncertainties, yeah, dealing with that. Yeah. And if you look at the periodic table, yeah, all these things, yeah, have fluctuating atomic radii. Yeah, all the elements in the universe have fluctuating atomic radii. Yeah, so when you measure a meter, yeah, and you tell us the assumption is that the meter has a constant length. No, it doesn't. If you was to look at it, no, it doesn't. Yeah, if you want a true meter, you can't say it has a constant. It has a constant part and a fluctuating part. The meter is also a two-dimensional unit of measurement. So even the unit of measurements you're using should incorporate fluctuation. Yeah, there's no such thing as a constant, a universal constant. Yeah, because we'll never physically be able to realize the degree of accuracy, yeah, in order to measure anything as being constant. Yeah. So if you're being practical, you have to say that there's no such thing as constants in this world. Yeah. That's basically the point I wanted to bring forward. Thank you.